Swayam Prabha. Digital India. Educated India.
Hello everybody, we are in module 6 on design and troubleshooting aspects of vacuum systems. These two are interrelated because when you design something, when you actually go to the system in practice, there will be some troubles. So, again you have to shoot the troubles and if necessary redesign systems in a small scale, and next time when you make a similar system you take that already into account. So, in this design aspects, in the last class we have seen some sources of gases which will oppose us not to get good vacuum. So, that is the duty of the designer to see to that these sources of gases are handled properly, the gases will be minimum as much as possible. So, that you will get very good vacuum and the output of the product for which we are designing the vacuum system is satisfied in terms of quality as well as production rate. So, that is the reason we did some problems sources that we normally encounter like outgassing, leaks and materials etcetera in the last class. Now, in this class we try to take a little fast recap of design aspects from the earlier lecture and then try to give some very simple equations which we have already given earlier, but from system design point of view I want all of you to know that these equations are very helpful to you in designing the system. Then how do you select various subsystems, whether it is pumps or components etcetera. Earlier we did selection criteria of pump only. Then we said some valves, but now you have to select all of them together because you are making a system. So, how are you going to do that? Then some design aspects of thickness calculations etcetera, which we have done earlier in isolation. Now, we have to do in a system approach and then how components to be chosen. Earlier we have taken components as components, their working principles. Here we are going to show how to choose those things. So, finally, you have to do all the works that a material scientist does, a process engineer does, a budget finance person does, and also the safety things and precautions to be taken and weight of the system and automation, instrumentation, everything is a part of design. So, those design aspects we will see at component level as well as chamber level, including fabrication aspects as per your design. You cannot leave fabrication aspects to some mechanic, you have to tell as a part of your design, okay. Whether it is brazing or welding, you have to design. If you say okay, you connect somehow, they will put some adhesive and you will not get even 10 power minus 5 torr, system is supposed to net minus 8 torr, pump is good, chamber is good. So, you have to also keep in track fabrication issues. We will see a small lab scale system that we normally use in research laboratories, and in the next class all these concepts together will be dealt in a example called vacuum metallurgical furnace. We have 20 sessions for applications, but metallurgical furnace I have taken because it operates around high vacuum level in between medium and ultra high vacuum, and apply all the knowledge that we have taken in these two lectures. So, that we have a step by step systematic approach of designing a particular application as a tutorial. So, in today's class we will only complete the microscopic as well as mathematical aspects in addition to selection criteria, so that all aspects of system design are completed. Then we will give some common conclusions covering both lecture number 36 and 37. You might have observed in 36th lecture I have not given conclusions, because that was part 1 of the system design, this is part 2 of the system design. We will give some common conclusions. Well, I again want your time for few minutes, which I have taken in the last class, showing various blocks of a good system design. Just for your recapping, I am not going to describe everything, this is just nothing but selections of pumps, chambers, safeties and necessary design aspects, conductances and various materials, components and instrumentations, okay, and shape of the chambers, volumes, all those aspects which you have discussed in the last class. I just want you to keep track of these issues in this class also, because this is a part 2 of the system design and this is a common slide for both the lectures. Okay. Once you understand these aspects, some aspects are small, some aspects are big, some aspects are mathematical, some aspects are electrical, some aspects are based on your experience, some pump down calculations, and even aesthetics matter when you make a vacuum system. You should not make it look shabby if your competitors make it very nice looking. Okay. And certain fundamental concepts you should be better than your competitors. For example, the surface smoothness is very important. You should immediately feel, because apparent area should approach the actual area, so that degassing is less. Thickness, optimum thickness, why? So that weight is less. So, what are the aims of design? To get good ultimate vacuum without process load on, that is ultimate. We cannot get better vacuum than that. That should be as low as possible. Like when you want to be very good engineer or anything, it all depends on what schooling you have done, college you have done, everything comes into that. Okay. Same thing here also. To get a very good vacuum, equilibrium vacuum with process, that is called with process load, you should also get a good vacuum without process on, that is called ultimate vacuum. These two things should be kept in mind. While doing that, you have to reduce the pump down time. You cannot get these good aims with 100 hours pump down. So, that depends on conductances and effective pumping speeds. How effective you are depends on how effective the pumping speed is at the chamber site. If it is not good, simply purchasing costly pumps, making very good chambers, very good feed throughs, shiny appearance, very good instruments here and there, but you do not get vacuum, or production time is very long, then it is of no use. Okay. So, you should take care of effective pumping speeds. Then minimum contamination, this is a very important issue in modern processes, particularly in pharmaceuticals and semiconductor industries. If there is a small impurity available as a foreign impurity which is not required, then the quality of the product will be totally down, even though you are getting very good vacuum for the sake of it. Pumps are running, chambers properly designed mechanically, electrically, instrumentation, safety, interlocks, everything is working, but contamination, whether it is water vapor or whether it is some lubricant that is coming out in robotics, which have to be there in UHV system, there may be small lubrication that should not evaporate, and there will be manipulators. How are you going to do? So, you should keep track of all those things here as components, but that time along with component coupling issue, you should also see degassing issues. So, the minimum contamination is very important, for which you should finalize materials properly, seals properly, joints properly, keeping in view the level of vacuum. Your seriousness may not be that high if it is medium vacuum, but if it is ultra high vacuum of 10 power minus 10 torr, you have to spend lot of time on these issues rather than pumps purchase or material purchase. Does not matter if you make a error in the thickness calculation, if it is ultra high vacuum, it will be little thicker. Do not make error in the other side. Instead of 5 millimeter optimum design, you have made 10 millimeter. It is okay, because 10 millimeter also will reduce the diffusion and permeability from all the way from outside. So, even if you have done mistake from mechanical strength point of view while designing a vacuum system, you gain something else. That is the reason in 10 power minus 11 minus 12 torr type of systems, even though they do not require that much thick wall, they still keep a very thick wall, so that polishing can be done easily without any buckling, and also diffusion from the gases already there in the material or permeation for the gases coming all the way from outside through the wall into the inside. All those problems are less, but it is heavy. Okay. Mechanically, it is not a proper design. That means, you are off design, but still it is a part of design. So, these issues you have to keep track, and also easy troubleshooting. If something goes wrong, the leak detector and RGA, they should be friendly to you. If possible, you attach a RGA with the system forever, a small component you can always attach, just like you can attach a scanning electron microscope to the ultra high vacuum system. After all, the system costs some 20 crore rupees. How does it matter another 10 lakhs of RGA or 20 lakhs of SEM, you can attach it, because you do not require separate vacuum for that. Otherwise, they require their own vacuum pumps. So, you can include those things. This is very important in system design. These are small issues which I have not covered in 36. There I have covered broadly degassing, pump down, schedule, where is diffusion, where is volume gas, like that. But here I am talking some finer aspects of it. Whatever you are trying to do should improve the quality of the process. Okay. Easy troubleshooting is a very important thing. And when you are using window materials, you should be extremely careful. You should not degas. Seals, in a ultra high vacuum chamber, it is the seal that is going to make the process dirty, because if you use some polymers or some gasket materials without your knowledge, somewhere some washer is used in some valve or something, you are gone. You might have made very good joints everywhere. Even if one small joint, if there is a polymer or some vacuum grease or some sweat is left over or a trapped volume is left over, which you have not taken care in the cleaning aspect of polished products at the sub-level assembly stage, you are gone. So, cleaning is also very important, and that who will do? Designer also has to know that. You say, it is not my headache, it is a fabrication. I have made some design, some electrical, mechanical. That is okay for some other applications, not for vacuum systems. The designer must know if there is a leak or if there is a degassing, what is the throughput, for which I have to design an excessive pumping speed, because I cannot avoid that leak maybe. There is no way, time is short. So, I have to do something, increase the pumping speed. Designer has to tell, the operator cannot finalize it. So, these are the issues. So, easy troubleshooting, and who will help you? Only the instrumentation and safety, automation and IoT can help you, because you are the designer, you are the master. Operator will listen to you, mechanic will listen to you, and outside other people who are handling water as a essential commodity for running the vacuum system, or power systems, electrical, they are all employed for the same system, but they will all listen to you as a designer. So, that is the reason you have to keep track of all these issues. There are many other microscopic issues we will discuss when we discuss individual applications. Okay. So, aims of the design are these. Okay. As I told you, unavoidable or avoidable or varieties of throughputs, all these things you have to keep track in a vessel, then welded joints, then couplings, then length of the in between coupling, the chamber and the system, very very important aspect. Do not underestimate this C. This will be few crores, this will be few crores, but this may be few thousands, enough to spoil all this. And everything is very good, properly optimized. There may be some degassing or leak or unnecessary evaporation. Necessary evaporation cannot be there from liquids in ultra high vacuum systems. They may be there in chemical applications. There it is not a problem, it is a throughput to be handled, that is Q is equal to S into P, that is the only throughput. But in ultra high vacuum, if something is evaporating, it is a junk for you. In ultra high vacuum, most likely you will use semiconductors or ions to be accelerated in nuclear applications, or a space simulation where the satellite is kept and tested for various maneuvers. So, there is no question of evaporation there. So, but in actual system it will be hidden, it will be there in the pocketed somewhere moisture. You have to handle all these Q's, then total Q should be equated to this. This equation I have given earlier and discussed several times, but system designer must worry about this equation very much. If everything is minimized, then this P will be ultimate vacuum. During the process conditions, this P will be equilibrium vacuum. That time that particular Q you have to take. So, Q is equal to S into P is the main equation for vacuum system designs. There is another equation for pump down times. This is not that important, because let it take, instead of 10 minutes, if you made a wrong design, 30 minutes, does not matter. But in a load lock chamber where you are quickly transferring silicon wafers and heat treating everything and make it clean and then transfer it through a magic arm and opening a gate wall, that time matters. Excepting that application, this equation may not be that thing. Of course, initial evacuation, basically this is pump down time, it is definitely good in sealed off devices making like bulb industry or X-ray tube industry, but it is not that important in chemical industry. Instead of 10 minutes, let it take half an hour. Once it comes, afterwards it is a load that is being pulled by the vacuum, equilibrium pressure, that runs for days together. So, how does it matter? Initially 1 hour takes 2 hours. So, this equation is very important in semiconductor industry, particularly for load lock chambers, because if you can put faster next chip, next silicon wafer, you will get faster chip production. Okay? Because initial evacuation to 0.1 tar and treating and ion etching, cleaning, holding and with a magnetic arm opening the gate wall, all these operations should be done fast. That is the weakest link. If you take longer time, you are gone. Does not matter even if you use little dirty pumps, you apply huge pumping speeds. Some people will think that I should have a very good pump and very stylish conductance as a nice looking things, may not be required. It depends on Q is equal to S into P. That place, what is the Q? In the fabrication issues, fabrication chamber, chip making, growth chambers, they are different, but load lock chambers, it is not important. So, here speed is important, like that you have to see, but whatever be the process, conductances have to be minimized. This mechanics will not understand. So, that particular throughput which is going to that particular element, whether it is a roughing issue or a backing issue, that has to be taken, that C should be optimized without getting into leak problems, etc. By you see, you cannot increase the diameter just like that to have a very good C, then that itself becomes a chamber, then you have to evacuate that chamber. Pipe should not look like a chamber. Sometimes people do that in over design. Then S effective calculations have to be done. Then you will have to see whether your application is a closed system like X-ray tubes, etc. Then you have to also have gettering actions and how fresh it is, that is a part of the design. They will just give you some sample of getter, you have to etch it and put it quickly in a oxygen free environment. So, they are very important. Similarly, if it is UHV chambers, how whether to use cryopump or turbopump, a very important decision. Then you see the residual gas analysis. If water vapor is coming huge, better to go for cryopump. Keep both those things. After all, process is very costly. How does it matter you keep one cryopump, one ion pump, one sublimation pump and one Hogger dry pump from the beginning itself, all these things, because you are not going to use all of them simultaneously, but valves isolating them must be UHV compatible. With a long in connecting pipe, if it is inevitable, then you have to over design the pump. Maybe you have to take a pump of higher pumping speed. That decision only designer has to take. Vacuum system design is coming in a policy decision now. So, you will have to convince other people to spend enough money to purchase higher things, higher pumping speed, because the inevitable long connecting pipes are there in that particular process. You have to do that. Okay. So, this PT calculation. So, this is must be small t, that means pressure versus time calculation, and SP selection, pumping speed versus pressure. This is a selection, this is a calculation, these two go hand in hand. Initial designs, once you finalize everything and also and with proper certification and with good manuals written to operator as well as repairer, then your job is over from the manufacturing. Then it is the headache of the customer, but you should also see to that he will not be in trouble, because he will call you back. So, this iterative design by the design engineer is very important. So, I keep on talking things again and again, you may be wondering, because vacuum system design means what? Good vacuum, that is all, and less contamination and cost effective pump selection and some special criteria related to process application for which you are designing, and of course, at the end budget. Okay. So, sometimes when you are having some wrong notions, then suddenly at the end you have to spend lot more money and lot more time. Time is also precious. Okay. And now in automation issues, IoT issues, you have to be equally good in selecting IoT related things. So, first pump, depending on the range you will have varieties of pumps available. Then you will have to take which one? One is pumping speed at the pressure at which process is operating, not pumping speed means what? Pumping speed variation. Then once you decide level of pumps, level of vacuum systems, level of components, then dry or wet, that means chemistry of the pump. Then you have to see electrical power requirements, chilled water requirements and effective pumping speed at the pump side, go back again calculate. So, selection of pumping things and materials is very important, and costliest part of course is pump. You have to keep track of that depending on the application cost. If application is a small bangle coating, then you can afford to be little impure, you can afford to be little delayed, things like that, because you cannot purchase costly things for a cheap application. Finance people will immediately object, you will not get gain, you will only get loss in the company. So, care must be taken in choosing materials for chambers, flanges, couplings and seals, keeping in track how much money you have to spend on this and what level of sophistication is required, what level of vacuum during process is required and what level of contaminations can be handled. You may get -7 torr, but it is having perfect contamination free vacuum, that is good. You may have -8 torr with a small contamination which is dangerous to that particular process, that is bad. So, these approaches you have to take in that practical sense. Similarly, surface area, apparent surface area is not the real area. So, you have to polish it very high. What level? It depends on the mean free path of that vacuum level. If it is 1 torr etc., you do not have to polish it very much, because most of the time collisions in the chamber dominate than the collisions on the wall. So, high polishing is not required, degassing will never dominate the process load. So, you do not have to worry, but you have to worry that degassing only and leak only at 10 power minus 10 torr. These things you keep track. Okay. Then chamber fabrication. Designer normally has got a tendency that fabrication is not my headache. No, nowadays you have to know everything, something about everything, and if you are a specialist in that, everything about something. Okay. But a designer, vacuum system designer, must be able to get a feel of fabrication issues like ASME section 8 vacuum vessel design, you should know, which we have discussed in lecture number 28 for making the thickness calculations. You may not stick to that thickness, but you should know 5 mm, okay, 8 mm, does not matter. Anyway, ultra high vacuum, so thickness more, diffusivity less, I will gain somewhere like that. Then you have to also see the structural strength. If it stands up to 1 torr, I told you that time earlier in classes, if it stands 1 torr, 760 minus 1 is same as 760 minus not 1. So, mechanical strength is done. You do not have to unnecessarily do strength calculations for 10 power minus 6 torr. Okay. Then from ultra high vacuum point of view, leaks, degassing issues, you should know the physics of degassing, chemistry of the degassing, what it is degassing. If it is degassing helium, how does it matter? If it is degassing argon, you do not care, let it degas, it is not going to interfere, it is not going to make compounds, because helium, argon, they are inert gas fellows, they are so inert, they will only be watching like your stainless steel chamber or any other manipulators. So, you have to be careful on that. And then these are all discussed already in earlier classes, like in lecture number 30 you can go back for degassing. Similarly, lecture number 29 fabrication details, what you should do, etc. Some standard components, you should not waste your time and energy and fund to make things at your place. Standard components to be purchased, but while purchasing, design properly. So, permanently mounted or demountable joints, you have to take care of that. Then cleaning also is a designed cleaning, whether you can use water cleaning or soap water or carbon tetrachloride or some other special cleanant or purging of the gas. If you are purging that gas load, who will remove later? You have to purge means fill it and again pump it. It takes some finite amount of time. You have to minimize that time. That is the initial preparation. That is a part of the design issue. Again, you have to have some pumps for only purging, some sources, leak gases. That wall should be UHV compatible. Anything coming into contact with UHV chamber from outside world, it has to cross the barrier of the vacuum chamber. There you have to be careful about seals and materials, components, tightening, torque to be applied, what much torque. If you apply too much torque, joints will be in trouble. Okay. You should not do that, o-ring will crack. Okay. You should apply that much torque, so that the metal gasket will start yielding, yield stress. If you apply too much, it may even crack, it will go to ultimate tensile strength. No, it should be only yield strength. So, all these concepts a designer should understand from the fabrication aspects. If you do all that, then you see how the complicated systems look like. A designer must keep track of all these things, flanges, couplings, pumps, so many pipes, gauges and seals, throttle valves, manipulators. You have to choose all of them properly, and then this manipulator design. Unnecessarily you should not purchase a costly manipulator, you require X, Y only, you do not require X, Y, Z and tilt and rotation. So, purchase decision has to be made by the designer, okay, and purchase from a good company. Otherwise, after getting here, the bellow will crack. Instead of producing a manipulation action, it will produce a leaking action. So, you should take care of that, particularly in ultra high vacuum systems like semiconductors or for photovoltaic, space simulation, particle accelerators, high tech metallurgy. There are metallurgies in different levels. Later we will see, for example, steel degassing at -2 torr type, -3 torr, whereas a very specialized alloy ceramic to metal joining that is done at minus 7 torr for interrupters. That is also vacuum metallurgy, this is also vacuum metallurgy, but levels are different. We will see all that later. Anyway, we are going to take vacuum metallurgical furnace in next class for making a system design approach from various aspects as a trial run. Okay. So, that is taken as a tutorial for you. And walls, whether you take needle wall or ball wall, flange connections, you have to take. While doing all that, the efficiency of the designer, I repeat, the efficiency of the designer lies in choosing proper chambers, proper components, keeping in mind the level of vacuum, the process requirements, its physics, its chemistry, its flow rates, its loading, its contamination issues, etc. Then production time, downtime for repair, contamination issues, and of course, finally, the budget constraints. Okay. So, you have to keep track, and where are these components available? You should try to minimize the budget. Okay. And from local sources, if you take, they can come immediately and repair. Suppose you take from a source far away, it will take 5 days for that engineer will come. So, you may lose time, but certain things you may have to purchase because they are not available anywhere. So, you have to keep track of all these things. A system designer must also know the supply chain management. Supply chain management in a short run, long run and emergency run, emergency times, you have to immediately supply. All these things, you have to keep certain things in your shelf. Suddenly you should supply like an emergency medicine. So, all these things a designer must keep track while assembling, while running, operating. Though operator will operate, you may not be there, but you will be remotely watching, and while troubleshooting, okay, and overall time management, budget management. That is how design plays an important role. It is nothing but what we have covered in the 35 hours only, but we are trying to recover it so that we know where we have to go before going into the applications. That we will also discuss little bit same issues in the next lecture when we discuss with metallurgical furnace as a tutorial of vacuum system design. For example, in a lab scale for a diffusion pump, a rotary pump and a roots blower and bypass valve and roughing valve or backing valves. This is a routine high vacuum unit most of the vacuum companies manufacture. They are available in research laboratories. This chamber can be a thin film growth chamber or a metallurgical furnace or a arc melting for things or a simple chemical distillation type of thing. These are small scale, but it also has got all the components like traps, baffles, pumps, lines, plumbing, valves, air admittance, gauges, ionization gauges, boosters when it is required, when it is not required, how to bypass. All these things you have to keep track. Similar system we will be facing when we are dealing with a vacuum metallurgical furnace. You can do 1-to-1 correspondence here. This is the system, this is the system. These are gauges, valves. Similarly, pumps, diffusion pump. Backside there will be rotary pump, roots blower, but with a bypass connection, because initial evacuation you have to use roots blower to boost the pumping, and then later you switch off, otherwise lot of electrical power requirement. Then safety interlocks, then mimic chambers. So, process, for example, this operator will be looking into that, but entire work was done by a design engineer. Okay. So, system design engineer is not here now, he is only operator. To make this operator friendly with all these things, designer has to keep track. If it is a furnace of minus 6 torr, but if it is a ultra high vacuum system, you have to keep track at various levels, components, joints, everything, and how they look like, what type of polishing has to be given inside. Outside also if you polish it will look better, you cannot put some paint, but inside polishing is sub-micron level, and couplings, joints, flexibility and design of interconnecting pipes, choosing the pumps in UHV chambers is a different game. That we will see when we are discussing applications. We have already discussed in the last 2 classes where we are doing system design, but a tutorial we will not do for UHV, we will do for minus 5 to minus 6 torr type of thing, a typical system for metallurgical applications of a furnace, vacuum furnace. So, with this let us give conclusions of part 1 and part 2 of vacuum system design. A comprehensive understanding is required for the designer. What operator is going to do, what a repair fellow will do, what the shop floor fellow will do, how to assemble, and what are the basic amenities required, water and pressurized gas like hydraulic couplings, some cylinders, and also power requirements, safety requirements including fire safety, and where to run out in the chamber when in the house if chamber gives some trouble, certain gases may be there which are in trouble. So, you have to keep track of it. Very big space simulation chamber, if there is sudden problem, it is so big it may even suck your shirt if you are suddenly nearby and you are in a hurry, you are in a worry, you try to close something and you are in trouble. Venting a large system, later we will see in the space simulation. If you make a mistake that you have vented when sound is reduced, you suddenly open the main door, but still you might have vented it to little over pressure. That over pressure into the door area is so enormous force, it will hit your face. So, all these aspects designer has to keep track. Fabrication issues with the reduction of outgassing and leak rates, but maximization of conductances, it is the headache of the system designer. If to the extent possible, you have to use the existing components available off the shelf in the market, but high quality components, so that you are limited to fabricating chambers and interconnecting pipes. Then at the end, you have to keep track of the beauty of the system, not only duty of the system, okay? Because what is this, it looks very odd, then first criticism will come to the designer, then only operator and all will come into picture. So, you have to keep track. Anyway, let us take an example of a vacuum furnace for metallurgical applications in the next class, where we will be discussing various types of design issues, keeping in track, I told you, keeping in track the process. Process can be melting or casting or a sintering or heat treatment. Okay. It may not be a brazing between ceramic and metal. So, I have to design keeping this into account. I do not have to bother about vacuum metallurgical aspects of ceramic to metal joining. I need not worry. These only routine components in any automobile industry. They need to be heat treated, but they cannot be heat treated in air. It is a heat treating furnace. Okay. Similarly, casting and melting some alloys, aluminum alloys, etc. That is another aspect of furnace, where oxygen should be less. So, the RGS signature should tell us do not melt now. And similarly, rotating couplings are required from outside to inside, because after melting you have to cast it right in the vacuum, and thermocouples, temperature measurements have to be done parallelly. Everything should be computerized, and beep signal should come, some alarm should come if something goes wrong. When you add some materials to be added when it is in molten conditions, or when you have to sample it for sending it to through a load lock or through a valve, you send it to another chamber where you will analyze the chemistry of it parallelly in situ has to be done. So, all these issues you have to keep track. We will try to understand these things with an example of vacuum metallurgical furnace. Thank you very much.